Here we have a RC circuit. We have a capacitor connected to some resistors and a source. We're being asked for I of t, which is the capacitor current, and then we also want V of t, which is the voltage elsewhere in the circuit. But that capacitor is going to drive the behavior of the whole circuit. In particular, the capacitor voltage is going to affect all these other values. So we're going to find the capacitor voltage first, and then we'll be able to use that value to find the capacitor current, to find any other voltages in the circuit. To find the capacitor voltage, the first thing we need to do is find the voltage before the switch is thrown, before changes are made to our circuit. Here we're told that the switch closes at t equals 0, so the capacitor only becomes connected to the source after t equals 0. So before t equals 0, the capacitor is not connected to the sources. We're told the initial charge on the capacitor is 0. All of these things tell us that the initial voltage for that capacitor is 0 volts because there's no charge and because the capacitor is not connected to the source. So the capacitor is initially with 0 voltage across it. Then the switch is going to close at t equals 0, so we'll have to analyze the circuit that we have after the change has been made to see what the capacitor does from then on. So here's the circuit that we have after the switch is closed. We have a connection right here. I've shifted the capacitor around and shifted the resistor around just to make the drawing of the circuit a little bit more convenient. If we want to know how the capacitor is going to behave, we need to look at what's happening to the circuit connected to it. We need to find the Thevenin equivalent circuit connected to this capacitor. And so what we're going to do is disconnect the capacitor and look at the circuit that's left over. Here we have the circuit with the capacitor disconnected from the terminals. If we want the Thevenin equivalent circuit, we need to find the open circuit voltage. That's going to be our Thevenin voltage right there. If this is an open circuit, then there's no current in this path. There's nowhere for it to go. So the Thevenin voltage here is just going to be the voltage across this 20 kilo ohm resistor. And we just have one loop here, so all of this current is going through that resistor, so we can find that Thevenin equivalent voltage. And we find the open circuit voltage is 150 volts. That's going to be our Thevenin voltage. We also can look in the terminals to find the Thevenin equivalent resistance. We need to deactivate any sources. So if we have a current source, the way we deactivate it is to make sure there's no current flowing there, meaning we need an open circuit. When we look in from these terminals, we have an open circuit here, so there's nothing going on. We have 20 kilo ohms and 30 kilo ohms in series, and so we can find the equivalent resistance there. So we found the Thevenin equivalent circuit connected to the capacitor. We found the parameters of that Thevenin equivalent circuit. The next step is to find the time constant, and plugging in the values for the capacitor and for the equivalent resistance, we can get a number for that. And now we have all the information we need to find the capacitor voltage. And so we were able to find the capacitor voltage as a function of time. That's what's driving the behavior of the whole rest of the circuit. Then we are asked for I of t, the current through the capacitor. Well, if we know the capacitor voltage, we can use that to find the capacitor current. This is the characteristic equation for the capacitor, and so we can plug in our known values to determine a function for the capacitor current. And so we're able to find the current as a function of time starting the instant after the switch closes. Then we're asked for V of t, the voltage across this resistor here. Well, we know the capacitor current is flowing this way. The capacitor current is defined in passive sign convention. We know the current flowing here, so if we can find the current flowing through that 20 kilo ohm resistor, then we can find the voltage across it. So we can use KCL to find this current through that resistor. And so we're able to find the current through that resistor as a function of time, and then we can use Ohm's law to find the voltage as a function of time. And simplifying, we're able to find the voltage as a function of time for t greater than or equal to 0 plus.